Good morning, everybody. Welcome to another exciting morning of Chem 1105 with your host, me, Dr. White. Back to acids and bases. We're talking about pH scale, which is probably one of the most important things not the most important things I'll teach you this semester. Remember, pH equal minus the log of the hydronium ion concentration. And if the hydronium ion concentration, H3O plus, equals 1.0 times 10 to the minus x, which is my special gift to you, it doesn't have to equal that, then minus the log of 1.0 times 10 to the minus x. When this is 1.0, then the pH is x. Now, you should know for pH, get the message? The pH scale goes from 0 to 14. In between is 7. At 7, you have neutral pH. That's when the hydronium ion concentration equal hydroxide. Below 7, we call that acidic. Hydronium is greater than hydroxide, and above 7, we call that basic. You should know that. The closer to 14, that looks better. The more basic. The closer to 0, the more acidic. Things that are acid taste sour. Lemons and lime contain citric acid. You bite into it and you go, ooh, was that tart? That's because there's an acid in there. The pH is less than 7. Why? Chem 1105 reason is the liquid in your and my stomach. I don't want to get personal, but I will. Why is the pH less than 7? Because it's acidic. There's an acid present. I won't ask this on a test, but it's a great miracle life to me personally that I have cells in my body that make hydrochloric acid, HCl, to make the liquids in my stomach acidic. Now, water dissociates, and because of that, there's a dissociation constant, Kw, named after me, I wish. Is hydronium ion concentration times hydroxide equals 1.0 times 10 to the minus 14. All right, let's go through the following. What is the pH of a solution if the hydroxide OH minus concentration is 1.0 times 10 to the minus 10? And is it acidic, basic, or neutral? Good question. What are we being asked to find? pH. What are we given? Hydroxide ion concentration is this. But pH, and this is an important information, test number 4, is this, which I don't have. How do I get this? Well, an important information, you have this. And in order to get this, when given hydroxide, guess what? You need 2 steps. Step 1, convert OH to hydronium ion concentration. Step 2, convert the hydronium ion concentration to pH. All right, let's do step 1. And the only thing we have to work with is this. But we also have this, which we're given. We want to solve for this. How do we get it alone on one side? We get rid of this. How do we do that? Divide by it, because anything divided by itself equals 1. Cancels out. And now this divided by this equals 1. So I have this. I can put in this value, which I have. Let's see if I have the right number. I do. So I'll pick up my calculator. Not. I can do this one in my head. Am I done? No, I have the hydronium ion concentration. I need the pH. So now I'll do step 2. If I can spell it. pH is minus the log of the hydronium ion concentration. We just figured that out right here. And now, remember when this is 1.0 times 10 to the minus x, this case x is 4, The pH is 4. So that's our pH. But we're being asked, is it basic, acidic, basic, or neutral? And you should know the following. You don't have to write it down, but I will. When it's 7, it's neutral. When it's less than 7, it's acidic. And when it's more than 7, it's basic. And I see a question, so I'm going to take a second, maybe a little more than a second. And the answer is yes. Let me finish this and I'll scroll back up and go through it. So pH is 4, it's less than 7, so this is acidic. All right. Jada, do you need step 1 or 2 to be seen? You're welcome. And let's go through this again. You're being asked to find pH. You're not given hydronium. You're given hydroxide. Important information. You're given pH equal minus the log of the hydronium. And also Kw, yay, after me, not really, is hydronium times hydroxide equal 1.0 times 10 to the minus 14. You need to do 2 steps. This is an important information. Test number 4. Step 1, hydroxide to hydronium. This is chapter 7 for those who are wondering. Acids and bases. Step 1, go hydroxide to hydronium. Use this equation, what Kw is equal to. Solve for hydronium. Put the numbers in, you get this number. However, this is hydronium ion concentrate 3O plus. You want to go to pH, H3O plus to pH. Important information, pH equal minus log of hydronium. Put it in, you get 4. Your acid is acidic or basic. When it's less than 7, it's acidic. When it's equal to 7, it's neutral. When it's greater than 7, it's basic. And did I time it good or not? It's time for a break. Come back in 5 minutes and we'll continue on. I'll see you in 5. Uh-oh, I'm running late. Better get going. Let's continue with acids and bases. By the way, tomorrow I will go through the acid and base problem set. All right, I've already covered this. Well, let's go through it again. Acid-base titrations. That's a neutralization reaction in which a measured acid, volume of an acid, or a base of known concentration is completely reacted with a measured volume of an acid or base of unknown concentration. And by doing a titration, you can find the molarity of the unknown acid or base concentration. Now, we use what's called an indicator, also known as a pH indicator, which you saw if you've done the Beyond Lab Z Lab. Remember, that's due tomorrow, changes color. And the most common is phenolphthalein, which changes color at pH 7. And I'm going a little faster because we've already touched on this, but I want to do it once more. And titration data are used to calculate the molarity of the unknown acid or base. At neutralization, you calculate moles of known molarity or acid or base, and based on this, you can determine how many moles and therefore the molarity based on the volume. All right, when you do a titration using a pH indicator, when the pH indicator changes color, you're at neutralization. What does that mean? You're at pH 7 when using phenolphthalein, and that tells you moles of acid equals moles of base. And what that really means is milliliters of acid times molarity of acid equals milliliters base times molarity of base. And in titration, you have milliliters of both acid and base, and you either have molarity of acid and you solve for molarity of base, or you have molarity of base and you solve for molarity of acid. And this will be given to you in important information test number 4. In fact, let's find out if I'm lying to you. I don't think so, but never hurts to find out. And notice, does everybody see on your screen important information? Make up thumbs, people. Come on, you guys are slow. Maybe you can't see it. And you can't. How can you see it? Yeah, sorry. Everybody see important information? Thank you, Rain. All right, now for titrations, notice this is important information. At neutralization, you know this and you know this. So based on those things, let's get back to work. Wow, that's a lot to write. If it takes, everybody see 10 points on your screen? Uh-oh, I better check. Yes, you do. All right, if it takes 352 milliliters of a 1.05 capital M HCl solution, remember capital M molarity, to neutralize 175 milliliters NaOH solution, then what is the molarity of the NaOH solution? So what are we trying to find? Molarity NaOH. What are we given? By the way, this is a base. You should know that. You should know HCl is an acid. And we're also given how many milliliters, 175 of the NaOH solution we need or we have. And don't forget that's still a base. So what do we do? It's a titration. Moles of acid equals moles of base. And if you look at important information, test number 4, I give that to you. And the next step you should know is this: milliliters of acid times molarity of acid, milliliters of base, molarity of base. Now I'm going to put the numbers in. We have 352 milliliters of acid, that's HCl, right up here, times the molarity of the acid here. We have 175 milliliters of the base times we're trying to find the molarity of the base. And now we solve for this. How do we solve for this? we get rid of that. How do we get rid of that? Divide both sides by that number, because anything divided by itself equals the number 1. This cancels out. I'm left with don't forget, show your work on a test. Now, I like to rewrite it. You don't have to, but I do. And good habits I don't change. Notice milliliters left out. I'm left with molarity, which is what I'm trying to get. And now pick up my calculator, turn it on, clear it. Then my calculator gives me this number. But this is 3 significant figures. Oh, I'm in my rut. 3 significant figures and 3 significant figures. So I'll let you round this off to, you're right, 3 significant figures. Keep the 2, keep the 1, keep the 1, use 2 to round off. It's 4 or less, drop it. So the correct answer is 2.11 molar NaOH. And that's how you use titrations. And tomorrow's lab, you'll be titrating an unknown solution with either HCl or NaOH and doing this. And that's how you do titrations. Tomorrow, I'll go through the acid-base problem set. I highly recommend you work on this and know how to do that. And remember, you're trying to find the molarity. You're given this, you're given this. At neutralization, you know this, which then means this. And now you put in the numbers, solve for what you're trying to find by dividing both sides by 175, do the math, and that's how you do it. Now, let's talk about something very interesting, and that's buffers. And buffers is a solution that resists major changes in pH when small amounts of acid and base are added to it. In other words, the pH really doesn't change. And buffers, which you don't have to know, but are acids and their conjugate bases of weak acids. So when you have a buffered solution, if you add a small amount of an acid or base, the pH does not change. You should know this. Hint, a buffer is not the definition, but be able to apply it. A buffer is a solution that resists major changes in pH when small, and that's the key, small amounts of acid or base are added to it. Hold on, time out for a spelling check. Oh my God, I was right the first time. Sorry about that. In case you haven't heard, I was always down, first one down in any spelling bee. And I blew this one. I had it right. All right, now I've finished. 2 points each. What happens to the numeric value of the pH of a buffer solution? And that's the important thing. Buffer solution, when you add a small amount of dilute, and notice small amount, and dilute HCl. Don't forget, HCl is an acid. And the answer is when you add a small amount of acid or base to buffer solution, there's no change in the pH or very little change for this class. I'll call it no change. And B, when you have a buffer solution and you add a small amount of dilute and NaOH is a base, what happens? Buffer solution, small amount of acid or base, no change in the numeric value of the pH. And if you see on your screen, not to scare you, but I will. But anyways, everybody see, human blood contains a buffer. And guess what? That buffer solution keeps you between a very narrow range of 7.35 and 7.45. If you go higher than that, like higher than 7.8 or lower than 6.8, guess what? You're dead. So why learn about buffers? It's in your blood, it's keeping you alive. And that's important because your blood, if the pH is too high or too low, or too low or too high, whichever way, I'll do it this way, too high or too low, guess what? Oh, you are dead. So our buffer solutions Important? Yes. I love doing that. Buffer solutions, that is. All right. Wrong thing. Oh no, look what it says. It's the end of this chapter. But before we end this chapter, I have to tell a story. It's time for a Dr. White story. I don't think I told this. If I did, somebody raised their hand and say you told it. I know I told it in the other class I teach at the other school. All right, when I moved into the house I live in now, uh, after about a couple of weeks living here, my kitchen drain was stopped up. It barely drained. I figured, what did the previous owners dump down there? Because I'm very careful. Don't, when your kitchen, put down any fat or grease down there, it'll clog up your drain. And being an organic chemist, I know that real good. So I called up my local rotor-rooter man. He came out, did his thing with his rotor-rooter, and it unclogged it. And I thanked him, paid him. I had a 6-month warranty or guarantee, whatever. And within about 2 weeks or less, it's clogged up again. Now, at that point, I'm working at a company where I have to go to work. So the money isn't the problem. It's me. I have to stop and stay home from work wait for this guy to show up. I got a lot to do at work. I was a senior manager at a major chemical company. And so he shows up, does the same thing. Within a week, plugged up. I'm not a happy camper, which is not a good thing, but all right, I called him up. He apologized. Third time, he brings this bottle of stuff. This will clean it out and I'll rotor-rooter. I said, give me the bottle. I'm an organic chemist, who knows? And I'll teach this in a little while this week. Surfactants. It's an area I've worked in. I looked at the bottle and looked at the label and said, this ain't gonna do much. It's more show and tell, not gonna get the job done. But he did it, unplugged it within a couple of days, plugged up again. I'm not putting anything down there but water and soap and stuff and hot water. And that's probably part of the culprit, but there's still a lot of gunk down there. So I said, I'm not going to waste any more time calling this guy, forget about the money. So what do? I go to my local Home Depot, and I'm not getting kickbacks from them, but it's a really good one by my house in the Schaumburg-Hoffman Estates area. And I have a whole wall of drain cleaners. And I asked, I'm looking at them, I'm picking up some bottles, and what the heck's the difference? And one, a nice gentleman, and there are a lot of nice women who work there too, comes up to me and, can I help you, sir? I said, do you work in this department? He says, yes. So all the drain cleaners up in this wall, it's like 5 shelves, it's like 10 feet long, it's huge. Which ones do the plumbers use? And I'm like, that. He says, that one. Which one is that one? Well, let's find out. All right, thumbs up, people. Do you see the black bottles that have the red hair and grease? Says Instant Power. Thank you. And he pointed to this stuff. Now, this stuff, of all the bottles on that shelf, lots of them, different brands, was the only one in a thick, heavy plastic Ziploc bag that had on the outside of the bag in red letters, please use safety goggles when using this product. And I looked at the label, and let's see if I can do this. And if you look here, it says sodium hydroxide and potassium hydroxide are the two main ingredients in hair and grease remover. Hopefully you can all see that, and you should. So I read that, and I go to the man and say, oh, it has a base in there, or bases. And he looks at me and says, no, those are acids. I said, sir, I have a PhD in synthetic organic chemistry. I know an acid from a base, those are bases. And he said, no, those are acids. Immediately I realized, why am I arguing with someone in Home Depot when I have a PhD in organic chemistry and know those are bases? He helped me, thank him, get it, go home and see if it works. So I thanked him. I went home, followed the instructions, except I let it sit in there instead of 15 minutes because it was real bad. I think I let it sit 45 minutes. I wore safety goggles just to be safe because the eyes are half the, and whenever you're dealing with hazardous chemicals, you should do that. I put on rubber gloves. I also have a lab coat, or you could wear a long sleeve shirt to protect in case something bad happened. You never know. And I followed the instructions other than letting it go. And lo and behold, clean drain. And I, just to be safe, I did it a second time. And for about 12 years, nothing. It slowed up, never really stopped up. And I keep a bottle of that stuff, a big bottle, if I don't need to, and poured some in, no problem. Now, it also works in the bathroom for hair that, not that I have to wear, I don't have that much to lose, but if you have a stopped up drain in the bathroom, hair is one thing. Another thing I'll teach you about too, but mainly hair stops up a drain. And I've had students and my brother-in-law use it, works like that. About almost 6 months ago, my bathroom sink in my main bathroom up here, it's over that away, was starting to stop up. I said, oh, it's time to get the hair and grease remover out. And guess what? Boom, it's like brand new. Actually, I should have done it years ago because it's better than it's, even when I moved into the house, it's even better than that. And I also, for safe, not safekeeping, but good practice, I did my bathtub too. That's clean like a whistle. Well, I don't know, is a whistle clean? Hold on. That's clean. All right. Story is, use that product. I've used it. A lot of my students have used it. Friends and family have used it. It works. Be careful with it, but it works good. And you don't have to wait around for someone like the Roto-Rooter guy who really can't fix the problem that could. The other thing I learned is don't argue chemistry in Home Depot, even when you have a PhD in chemistry. It's not worth it. Don't. Once, a couple years later, when I was picking up some, those little white pellets, calcium chloride, because they were going to have real bad ice storm coming, guy was buying something else, and which was, I'm going to sneeze again. It's a slow developing sneeze. It's slow sneeze Monday. But anyways, he was buying a product that was 50% sodium chloride, 50% calcium chloride, and I think it was a 50-pound bag, was cheaper than what I was buying, 50-pound of all calcium chloride. Calcium chloride melts things better at a lower temperature. He said, no, buy this, it's cheaper. I said, but this does better. He started arguing with me, not arguing mad, but no, this is better, it's cheaper. And I said, all right. And he went away. I bought what I want. And I finally realized, get it in your brain. Do not ever again debate chemistry in Home Depot. Not worth it. But at Home Depot and Menards too, they're very friendly, and also Lowe's, not to leave them out. All right. Any questions about acids and bases? All right. Well, it's time to talk about organic chemistry, which I'll be talking from chapters 9, 10, 16, 17, and 18. Now, I should tell you a couple things. One, you're on my home court now. I'm an organic chemist. Two, in a couple hours, I'm not going to teach you all of organic chemistry. Right now, I'm finishing up the last week at the other school of an 8-week summer, which is at COD I've taught, and at Elgin Community College I've taught a 16-week semester survey organic chemistry, and that just touches the surface. Any topics I talk about right now, I could probably do a whole year semester graduate level courses, but we're just going to give you enough, but it will help you learn about organic chemistry, and it'll be on test 4 and the final. Isn't it nice how I make things relevant? Points, I want it. All right, let's talk about organic chemistry. What's organic chemistry? Before I answer that, thumbs up. How many of you have heard about organic food? Guess what? Really, organic food, that term organic, has been hijacked by marketing, sales, mainly marketing departments of various food companies to mean, ooh, this is insecticide, pesticide, and other harmful chemicals free. In reality, all foods are organic, except now we're using that adjective organic foods to mean something for salespeople or to get you to buy some. But what does the word organic mean, or organic chemistry? Well, initially, organic chemistry got its name from study of molecules that were in living things like plants, animals, and us, humans. But about 1808, a German chemist made an organic molecule from something inorganic, from molecules that didn't come from things that were alive. And that means you have to change what is organic chemistry. And now organic chemistry is the study of molecules containing carbon atoms and other atoms, mainly hydrogen, oxygen, nitrogen, and other things too, but those, mainly those. Now, there's something special about a carbon atom. A carbon atom has 4 valence electrons. And you learned that earlier. Remember, valence electrons are the outermost electrons of an element. And because of this, and this is the amazing part about carbon and why it's my favorite element on the periodic table, well, I'm an organic chemist, it can bond to other elements, and this is important, including itself. It can form long chains with and without, and I'll teach you this, branches or rings. And it's the basis for all life on Earth. If we didn't have carbon, we wouldn't exist the way we do today. Would we exist at all? Good question. I don't know. Now, when we talk about carbon, your skin is made up mainly of carbon atoms with hydrogen. Your skin is a huge organic molecule. My cotton shirt, organic molecules. My hair and beard, what's left of it, is organic molecules. And most things are. Piece of paper, organic. Plastic pen shell, organic. My monitor, mostly organic molecules. Not the water in here, but the plastic bottle. That's organic chemistry, organic molecule. It's everywhere. And you know who's the greatest of all organic chemists? Mother Nature, and I mean that sincerely. The stuff she's done is amazing. your skin, your hair, cotton for your clothing, a whole lot of things. Just look at trees and anything growing outside or inside your house. If you got plants or animals or us, that's all organic chemistry. Now, there are a couple of definitions I would like you to know. And if you've been following the discussion about pollution and climate change, these play an important role, not the only role, but an important one. And the first one is hydrocarbons. What are hydrocarbons? Those are molecules with only carbon and hydrogen atoms. So if I say they're hydrocarbon pollution, I'm talking about molecules that only have carbon and hydrogen atoms. And that is a source of pollution that's causing global warming, hydrocarbons. Now, when we talk about hydrocarbons, there's two types. The first type we call saturated hydrocarbons. If it's a hydrocarbon, that means it's a molecule with only carbon and hydrogen atoms. And it also means in which all carbon bonds are single bond. Remember, single bond, one pair of electron, double bond, two pair, triple bond, three pair. So saturated hydrocarbon is a hydrocarbon, meaning a molecule with only carbon, hydrogen atoms, which all carbon atoms are single bound or single bonds. Now, the other type of hydrocarbon is unsaturated. Unsaturated hydrocarbon, it's a hydrocarbon, so it's a molecule that has only carbon, hydrogen bonds, atoms, but now it contains, and this is important, one or more carbon-carbon multiple bond, which we mean a double bond or a triple bond. So unsaturated hydrocarbons have carbon hydrogen atoms, but a double or triple bond and also carbon-carbon single bonds, but a saturated hydrocarbon has only carbon-carbon double bonds and it has only carbon hydrogen atoms. How many of you have heard of saturated and unsaturated fats and oils? No one? Nobody's heard of unsaturated fats? Why? You got at least one, two, some of it. Is this, I don't want to use my thumbs up Monday? All right, now, same thing, and I'll teach you later on. Saturated fat has only carbon-carbon single bonds in a fat or oil, like vegetable oil, or unsaturated fat or oil has at least one carbon-carbon single bond. And I'll go over that later on. A triple bond is something, carbon-carbon triple bond is something organic chemists came up with. In all of the stuff Mother Nature did, she's never created a molecule with a carbon-carbon triple bond. Now, nitrogen has a triple bond, she did, but not organic molecules. Interesting, but true. So there's hydrocarbons, molecules with only hydrogen carbon or carbon hydrogen. There's two types that you should know. Saturated hydrocarbons, because it's a hydrocarbon, it has only carbon hydrogen atoms, but because it's saturated, all carbon-carbon bonds are single bonds. Now, unsaturated hydrocarbons are molecules, again, because it's a hydrocarbon with only carbon hydrogen atoms, but because it's unsaturated, it contains one carbon-carbon double bond or triple bond, or more than one. Now, one of the most amazing and powerful and wonderful things about organic chemistry is what we call functional groups. I'll never ask you what a functional group is, but it's a specific group of atoms in a molecule. And the beauty, and it is beautiful, now you know I'm an organic chemist, functional groups, if they're in one molecule or a different one, when you react it with a certain reagent, it always undergoes the same type of chemical reactions. And that's why we learn functional groups in organic chemistry, because those are the key parts of a molecule that we use to make new things. What new things? Well, did you wash your hands in the last day? I hope you did. The soap you use, whether it's bar soap or liquid, was made by organic chemistry using functional groups. The food you eat that Mother Nature did was made by using functional groups to make bigger things. When you chew and swallow and it goes in your stomach, the functional groups in your food are broken down into new molecules to help your body grow. Now I'm way beyond my knowledge of the human body to do things, and that's all functional group chemistry. What's a functional group? Now I'm going to come back to this slide. Now, again, functional group reactions are a reaction of a certain type of functional group to yield the same kind of product most of the time. There are sometimes exceptions. By the way, the letters I.E is Latin for that is. Now, this is important. How to find a functional group in a molecule. Look for anything that's not a carbon atom or a hydrogen atom or carbon-carbon single bond, and that will be a functional group. And that's where the fun is. That's where all the action is. So how do you find a functional group? Look for what's different in a molecule. What's not a carbon atom, a C, hydrogen atom, H, or a carbon-carbon single bond. So let's back up. Now, there are a whole bunch of functional groups. And the first one is a double bond. And a double bond, in organic chemistry, we don't use Lewis structures. We use what's called the line structure, which I'll be teaching you. Now, a double bond we show by two lines. And one other thing I'll be teaching you in a little while, but I'll mention it now. There's always 4 bonds to carbon. I teach this organic, always 4 bonds to carbon. Does this look like it's coming at you? 4 bonds, 4 bonds. I'm ambidextrous, so I can do it with both hands. There's always 4 bonds to carbon. If you find a difference to that, let me know. We'll be rich beyond my wildest dreams, which is beyond my own Lamborghini and Ferrari, beyond that, beyond my own fighter jets to play with, and beyond my own islands in the South Pacific. Much more than that. What I'm trying to say is it doesn't happen. There's always 4 bonds to carbon. All right, let's look at something. When I teach organic chemistry, I tell students to ask the following question. why are you learning this? Or you should ask, why am I learning this stuff? Well, the obvious answer is when you take organic chemistry, you want to get a good grade in that class because somebody told you you needed to take it to get into a program or a school. Organic chemistry classes are required for like nursing. Oh, really, why should you learn it? Let's look at one. Let's look at double bonds. But first, I've got to ask a question for all you thumbs up people. How many of you have seen a carrot or a slice of carrot in your life? Oh no, I mean, you haven't seen a carrot? You don't know what a carrot looks like? All right, some of you are being honest with me. Well, thank goodness for Google. All right, can everybody see carrots on your right side of the screen? For those who've never seen a carrot, look what color it is, orange. Why is that orange? Ooh, it's because of the following molecule. Now, the molecule that makes carrots orange is called beta carotene. Does everybody see all those lines on your screen now? Thank you, Ashley. Right here, each bend in the line is a carbon, each end of the line is a carbon. And where you see two lines, like right here, here, or here, that's a carbon-carbon double bond. And this is called beta carotene. How it got that name? That's called the common name, not an official, which I'll teach you, IUPAC name. But beta carotene has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 double bonds in it. And it absorbs all the colors of the light except the ones that make orange. And that's why carrots are orange. Now, your body breaks down beta carotene to make another molecule that has a common name called retinal. Sounds like something in my eye. It is. Your body uses retinal for your retinas, help you see better. And that's why Bugs Bunny sees so well, because of all the carrots he eats. How well those carrots help your eyesight? Don't know, but are there other sources of beta carotene? Yes, but I can't think of one right now. Carrots are the best. So when they say carrots are good for your eyesight, there's a fact behind that. Double bonds. So why are you learning? And that's a functional group. Boy, time flies when we're having fun with pH titrations and organic chemistry. There. And with that, I'm going to say, gang gesund, goodbye. Don't forget, if you have any questions about anything, come to my office hour tonight. Goodbye. The fancy goodbye. The fancy goodbye in stereo. Thank you. All right, Rain, I'll see you later. Any last questions before I log off? All right. And I should have mentioned it. I'll do it tomorrow. With that, Dr. White logging off from COD East, or actually COD Northeast. Bye now.